I want to talk today about the rates of chemical processes. And when we're studying the rates of a chemical reaction, we're looking at what is called kinetics. Kinetics is looking at the movement of chemicals and how they change going from reactants to products, and then the speed of that process and what factors go into changing the rate of the process. And so one of the ways that we understand matter as chemists and the way that we understand chemical changes is through what is called collision theory. Collision theory is the idea that any chemical change has to be the result of colliding particles. So we're talking the physical collision between particles. Particles are colliding together and then chemistry happens, but they have to do it with sufficient energy, otherwise that reaction won't occur. So if we think about this chemical reaction, this is a double displacement or a double exchange reaction or a metathesis reaction. So if I have a reactant AB and it reacts with CD, and these two things are going to collide together, right? And if they do this with a sufficient amount of energy, then we're going to be breaking chemical bonds. So let's think about it from kind of a Lewis dot-esque looking kind of structure. So I'm essentially breaking the bond between A and B and C and D, and then they're rearranging, they're swapping partners. So I end up with kind of this reforming when they come away from this process, this reforming then of our AD and our CB. So what had to happen then? Well, bonds had to break, bonds had to form. So we have breaking bonds over here, to be confused with Breaking Bad. And we have forming bonds over here. And it requires energy to break bonds, right? I have to put energy in order to break bonds, and that energy comes from the collision of particles. And it's kinetic energy then. So that kinetic energy of those moving molecules, those moving particles, is going to cause these bonds to break, so long as there's enough of it. And then when these bonds form, energy comes out of the process. And so if you've seen some of my other videos, you know that this energy in versus the energy out, let's kind of do that. The balance between these two energies gives you the overall change in energy of a chemical reaction. So we have kind of an enthalpy on one side, an enthalpy on the other side, and the overall change in energy, the energy out minus the energy in, gives you your delta H, which is your enthalpy or energy of the reaction, enthalpy. So if we were picturing this on kind of an energy schematic, if we're thinking about this graphically, because we do, because we're scientists. So here's our energy on the Y. If we have reactants here, so here's my AB and my CD, and I have products over here, so here's my AD and my CB. Then when these two things react together, they collide together, then the bonds break, and for a moment, then there's kind of this weird high energy intermediate step where there's a bond that's breaking between my AB, there's a bond that's breaking between my CD, there's a bond that's forming between my CB, and a bond that's forming between my AD. So there's this weird kind of like Frankenphase in the middle here, where we have this kind of super high energy, super transitory state that is between reactants and products. So we had to put a lot of energy in to get up to this stage, and then it's kind of all downhill from there. Once we get to that ugly, awkward, uncomfortable phase, then we're back down into products, which then release some amount of energy, because this is a lower energy state than these high energy, uncomfortable molecules. This state in the middle is called, it's either called the activated complex, I've seen it called that. I like transition state better personally. So the activated complex or transition state is kind of this weird intermediate between my reactants and products that's super high energy, super short-lived, because it doesn't like to be up here. It doesn't want to be high energy. It wants to be the lowest energy possible. And so this kind of looks like that hill that we've talked about. You have to overcome this hill in order to get from one side to another. So if these are my reactants and these are the products, that hill that I have to overcome going from reactants to that high energy activated complex in the middle is my activation energy. That's that minimum energy that's required to overcome that barrier. So in the same way that when I need to roll a ball up a hill, if I don't put sufficient energy into pushing that ball up to the top, then it is going to just roll back down. But if I can get enough energy just to get it to the top, then its own inertia, its own internal energy of the system is going to cause it to move forward. So it's the same kind of idea with our reactants and products here. Okay, so that's our collision theory. This is the general idea that these particles smash into each other, the bonds break, we get energy out when bonds form, so there's this balance of energies, and we can kind of map out what that energy looks like. If we look at the way that this one in particular is mapped out, I had to put more energy in than I got out. We'd call this an endothermic reaction, or an endergonic reaction. So more energy in than we get out. But anything, if we're kind of bringing this back to rate or speed, anything that's going to increase the number of collisions that we have, that increases the number of bonds that I can break, is going to cause this reaction to occur more quickly. So let's talk about those different factors. So let's talk about kinetics a little bit more. So kinetics all comes back to collision theory, because anything that increases the collisions is going to increase the rate of the reaction, because collisions equal chemistry. So the most obvious one that tends to come to mind is, okay, well, if I want to speed things up a little bit, I can increase the temperature. And we know that that's going to cause more collisions, because an increase in temperature causes an increase in the speed and the motion of particles. That's another model that we use to describe matter, the kinetic molecular theory, right? Everything is always in motion, and there's this direct relationship between the temperature and the motion of the particles. So if I speed up the motion of the particles, that's going to increase my overall rate, because I get more collisions. Another thing we can do is, if I want more things to collide together, I can put more things in there, right? Like I could change the concentration of my reactants. And if I increase the concentration of my reactants, then I have more stuff colliding. So greater concentration, there's more stuff in there, or you can think about it as less space for more stuff, that kind of thing. So concentration of reactants. So there's kind of a couple of ways we can do that. We can either increase the amount of stuff, so we'll call that of reacting species. But another way I can increase the concentration, so I'm putting more stuff in there, but I could also decrease the volume. And both of those functionally will increase the concentration of the reactants. I'm either increasing the amount of stuff or I'm decreasing the volume, which functionally will increase the concentration. So both of those have that kind of impact. The next thing that impacts the rate of the chemical process, again, thinking about collisions, is the shape of a molecule. So molecular shape, or the orientation of the molecule, so the way that it is oriented in three-dimensional space. So molecular shape, or the orientation in space, you have to have the right part of the molecule that is in the right area to collide with the right side of the other molecule, right? So we have to have the right side. And I'm going to put side in kind of air quotations here. I like to think about it like Velcro, right? If I have, there's sort of loops and hooks in my Velcro, and so if I have the loops on one side and the hooks on the other, then they'll stick together, right? But if I have loops on one side and loops on the other side, then they're not going to stick together. So the shape and the orientation in space are going to matter, and they have to be pointing in the right direction to where, when they collide, then the right things are interacting with each other. This is something that we have less control over as scientists. So if we're thinking about trying to do this in a lab and conditions I can control in the lab, part of it would maybe just be choosing the right reactants in order to cause the most efficient reaction, but I can't control how two individual molecules react together. We're not there yet, or at least I'm not. All right, another thing that will increase the rate of the reaction is the physical state or the phase of your different reactants and products. So the greater the motion there is between these things to move around, so the greater the degrees of freedom, then the greater the rate. So if we're thinking about different phases that have a greater amount of freedom, of course gases immediately come to mind. Liquids tend to move faster than solids do. Solid state reactions tend to take a very long time, or you have to cook them at really high temperatures, so you have to do things, you have to change a lot of these different things in order to speed up a solid state reaction. So the physical state matters. Physical state, of course, can also include solutions, right? So if I have a solute that's dissolved in a solvent, then that gives you, and that solvent is water, that gives you an aqueous solution. So if something is aqueous, then that has a little more freedom of motion than just the individual compounds on their own as well. Now the fifth thing that can speed up a chemical process is something called a catalyst. Now you've probably heard the term catalyst before. We use the term catalyst in everyday speech. You can talk about people as catalysts, right? They could be catalysts for change. And what we mean by that is that they cause something to happen more rapidly than it would naturally without their influence, right? So a catalyst is something from a chemical standpoint that does the same thing. It's a substance that speeds up the chemical process. And kind of the cool thing about this, or the bad thing, depending on whether or not this is a good or a bad thing for your reaction, is that it doesn't actually get consumed in the process. And the reason that that's important is because it's not just a one and done kind of operation. I throw one molecule in there, it sped it up, that's it. It's I throw one molecule in there, or one atom, or one ion, or whatever it is that I'm using, and that same one is going to go on and speed up the process over and over and over and over again. So the catalyst is really important. And the way that it does this, the way that it is involved in this, is by giving a different reaction pathway. So let's look at our energy diagram again. So here's our energy on the Y. And if we think of kind of reaction progress along the X here, so this could be time or reaction progress. It's kind of a visual. Then if we have reactants here and products here, and we have that weird awkward transition state up here, where we have kind of our bonds that are breaking, bonds that are forming, really high energy. So our reaction trajectory would look something like this. Whoops, too far. So it's going to go kind of, there's my hill. Now a catalyst is going to come in, and the blue versus purple doesn't show up very well, but I'm doing different colors just for my own sense of color scheme here. Okay, so a catalyst would actually give you an alternative pathway. So there's something about these reactants that add into this catalyst and then they form the product. So it gives it this alternative chemical pathway that lowers the amount of energy. So this has a specific activation energy that's associated with it, and this one has a specific activation energy that's associated with it. And that catalyst decreases the amount of energy that is needed for the reaction to occur. Because that activation energy is the minimum energy required. So if I can lower that amount, that will functionally speed up the reaction. So these are 5 different things that can help to speed up chemical processes, a little bit about kinetics, kind of building on our model with collision theory. And we'll talk a little bit more about how this then can relate to multiple chemical processes and kind of the interaction between forward and reverse reactions in future videos.